Okay, I'm going to talk about three of the simple machines and how you do mechanical advantage calculations with them. In some respects, you really only have two equations the whole time, or two formulas the whole time. Effort over resistance for IMA and the distance, and then AMA is resistance over effort with regards to force. So the actual mechanical advantage, you divide the forces. The ideal mechanical advantage, you divide the two distances that are involved. Okay, and so the first thing I wanted to talk about is levers. That's the first 9 problems in your activity that you have to do involves first, second, and third class levers. So first class, well, let me get a pin out here, is first class lever is the top one. And how that works is that it's a first class lever when here's the fixed point. This is called the fulcrum, and you have forces going on either side of it. Okay, and it's a first class lever when the resistance force and the effort force on opposite sides of the fulcrum, the distance to the effort force and the distance to the resistance force are given right there. Okay, and so that's a first class lever where, you know, an example is a seesaw, or actually a crowbar to take off, would be another good example of a first class lever. Or if you ever try to take the lid off a paint can, the little ruler looking thing that you use to try to take the lid off the paint can, that is a first class lever. Okay, one in which the mechanical advantage is really big. Okay, and then here is and I lost my pen somehow, is a second class lever. This is what these are called. An example of that would be, well, the one in the example in the activity is a wheelbarrow, right, where this is the force that you have to of resistance, the resistance force, all right, and then this is the effort force. So you're holding the end of the wheelbarrow, and there's a bunch of weight in the middle here, and so you have a much larger effort distance and a much small, compared to the resistance distance. So let me go ahead. Let me pause it and put all the stuff where it needs to be. So here we go. Here's everything labeled. For wheelbarrow, which is a second class lever, or any other second class lever for that matter, the resistance force is closer to the fulcrum, so dr is this small distance, de is this big distance, the effort. Okay, the mechanical advantage is always bigger than 1. So in a second class lever, you always get a mechanical advantage and it is bigger than 1. For a third class lever, it's vice versa. Mechanical advantage is always less than 1. Examples of of third class levers are something like some tweezers, where your fingers are in close to where it's bending, and then what you're trying to hold is at the end. Or something like your jaw, where the food is at your teeth near the front of your mouth, but the muscles that are opening and closing your mouth are much closer to the back, and so the muscles that are opening and closing your mouth, that's the effort force nearer to the fulcrum, that's at the beginning of your jaw. The food you're trying to crush mercilessly in your mouth is more towards the front, so that's a third class lever. Right? So anyway, these are the 3 types of levers, and all these formulas work for any of these types of levers. Okay? And so what you do in the problems in the activity and in general in a quiz or the end of the year final exam, you pretend that IMA and AMA are equal to each other if you're trying to use information in a problem to find, well, basically anything in the homework, you'll have 3 of these 4 given to you, and you have to find the 4th one. All right? And so if you go from here, this is saying that AMA is equal to IMA. Okay, if you cross multiply that sucker, it gives you this. So going from here to here it's cross, whoa, that was not supposed to happen, cross multiply. Okay. So let's do an example of calculation you might do. This is so you have a crowbar, which is a first class lever. So the fulcrum is right here. You can see a couple different pictures I found on the internet. Fulcrum is where it's curved, and then the effort distance is this. Okay. So this picture here, it looks like they're roughly the same, but it actually could be, one could be way bigger than the other one. As long as the fulcrum is between the two forces, that's all that matters for, first class lever. And so the effort is this big long thing, DE. Alright, so I paused to bring on the labels because that was smarter. But yeah, D is the big long thing and DR is the little guy, which is, well, that tells me that DE is 1.6 feet and DR is 0.2 feet. And then the effort force is how much you put into it. So that's what you're doing at the end. So I'm going to pretend, we're going to pretend it's right at the end of the handle. That's FE. So let me actually start typing stuff or writing stuff in. So the effort is 1.6. The effort force is, I'll use parentheses, 15. And I don't ever write units until the end. DR is the 0.2, and the FR is what you're being asked about. How much could you pry off with this crowbar or pry bar? Okay, and then so boom, just a little bit of algebra. So 1.6 times 15 is 24. And then you divide both sides by 0.2. Alright. So 0.2, 0.2. Okay. Is your FR. That's 120 pounds. Is what that works out to be. Which is a lot. So not F2, what am I doing? FR. Let me fix that real quick. The force you can overcome, the resistance force, or sometimes that's called the load force. I'll include that in there because it's in the picture over there, and that is what it's called sometimes. FR. Alright, so there you go. There's levers. Hopefully that's enough to help you a little bit with levers. Those are the first 9 problems in your activity. So another concept that is, actually this is throughout all the mechanical advantage stuff, all the simple machine stuff, is the idea of efficiency. And so we have actual mechanical advantage and ideal mechanical advantage. Actual is always less than ideal because there's some inefficiencies due to a lot of times just friction or something. Alright? And so to find the efficiency, it really is just this one little calculation. So let's say you do a problem and you have an AMA, you figure out the AMA, and it's 4 to 1, okay, or 4. So sometimes you see mechanical advantages expressed as ratios, so I thought I'd throw that in there. So that's the actual mechanical advantage, all right, but due to some sort of inefficiency in your simple machine or even compound machines, whatever, you can talk about the efficiency of any sort of machine, you get, right, so you get an actual mechanical advantage of 4 to 1, and then an ideal, let's see, you calculate the ideal, and you get 5 to 1, which is 5. So the efficiency is 4 over 5 times 100%, which is, well, 4/5 is 0.8, so you get 80% efficiency. No big deal. You can just divide the mechanical advantages and multiply by 100%. Alright, wheel and axle. So, wheel and axle, notice it's the same formulas. Okay, IMA and AMA, it's the same formulas. So let me go ahead and label what those are. I'll pause and label what those are on our, well, this is the wheel, or excuse me, the big is the wheel and the axle is little guy, okay? Alright, so this is misleading perhaps because how I've drawn it is that the distance is always the distance from the center to the outside of the axle, and the force is always applied at that. Okay, and then same thing, so this is the effort force. Well, that's not how all wheel axles work. An example of a wheel axle that would work like this would be a doorknob. This looks a little bit like a doorknob, right? Where you're turning it at the outside, and so the effort distance is from the center to the outside, and the effort force is being applied at that spot. And then the inside, the actual thing that's turning, you know, the thing that unlatches the door, is the axle part on the inside, and that's where that's DR and FR is measured there. Thing is, it could be vice versa. Okay, if another example of a wheel and axle would be a literal wheel and axle that's on a car, and these would switch places. So you have to figure out which one's which. Okay, depending on the context of the problem. So what effort is being put in is always, or you know, what force is being put in is always the effort force, and where that's happening is the effort distance. Okay, so it's always you look at the radius or the diameter. Okay, and the reason why that works is that, well, basically IMA in reality is the distance traveled, and that is equal to 2 pi little r. Okay, or let me do that. Not little r. Let's do r at the effort. You know, wherever the effort is being applied. So how the picture is now, that is the little r over 2 pi times r, where the resistance. So that's confusing. R resistance is what that means. And check out what happens. Boom, boom. Okay, and so it's the radius over the radius. 2 pi's cancel out. Or the diameter, I'm putting d for diameter, that might be confusing, it's not d for distance here. Diameter over the diameter. Alright? But keep in mind, that's just how I've got it drawn now. These could be switched. It depends on, if this was like a real wheel, like on a car, then this is what you would do. The diameter of the diameter radius of the inside axle goes over the diameter radius of the outside axle. And last but not least, pulleys. All right. So for time reasons, I'm accelerating the pulley part, and really, here we go. You might want to pause it to see where I got all these numbers. So if you calculate the IMA, here's the deal with this picture. It's assumed to be kind of an ideal situation. So what's up is that the IMA and the AMA are the same in this little scenario here. All right, it's kind of shenanigans, but it's going to illustrate a point. So if you look, 100 newtons is being pulled. This is called a fixed pulley, and in a fixed pulley, all that ever does is actually just change the direction in which you have to pull in order to move the object. And it is actually always, this is a fixed pulley because nothing's moving other than rope and the weight. The mechanical advantage is always 1. Notice here, like I said, you might want to pause it. 50 and 50 to overcome the 100 total pounds of weight, so you only have to pull 50 pounds. 33 and a third, 33 and a third, 33 and a third, and this movable pulley, so you divide that out and you get 3. Everything's chopped up into 4 parts, so 25 apiece to overcome the 100 newtons. If you look, the number of strands that are directly attached to the moving part tells you the mechanical advantage. So it really is the easiest formula around. You count the number of strands that are attached to the weight that are actually in the movable part of the pulley, and then voila, that's your ideal mechanical advantage. And if it's some sort of magic pulley where it's perfectly efficient, then that would be the same as your AMA. And so these are magic pulleys that don't exist in real life, but that makes the math really easy to do. So your AMA, you have to divide the forces, and so we use that to figure out, well, that what your IMA has to be 1, 2, 3, and 4 for 1 rope attached, 2 ropes attached, 3 ropes attached, 4 ropes attached, and that extends to how many ever ropes have happened to be attached to the actual pulley or to the weight. All right, so there you go.